So, good evening, ladies and gentlemen. So, the weather is beautiful outside. So, on this beautiful evening, I am pleased to welcome each and everyone to a brainstorming webinar on the very trending topic robotics and artificial intelligence and interdisciplinary tale by our alumni. So, come, let's take a step ahead in our passion. So, this is your host, Vaishaki Chakravarti, representing Robotics, the official robotics club of Netaji Subhash Engineering College. So, from dumb factory robots to self driving cars, robotics have come a long way. We are fascinated by the wonders of robotics and artificial intelligence. So, wondering about this evolution, we are here to hold a very interesting session on the trending topic. We extend a warm welcome to Mr. Sayan Paul, developer at TCS Research and Innovation, along with Mr. MD Nasirul Haque, who is developer at TCS, for gracing this event with their presence. They happen to be very prominent alumni of Robotics, that is the official tech club of official robotics club of Netaji Subhash Engineering College. So it's going to be a very informative session as the itinerary is very exciting. So come, let's enjoy the session. So I would like to welcome Shayunda and Nasirulda on board.
Hello, everyone. I hope you all are uh, at home and staying inside and safe. So today we are going to present you with this topic: robotics and AI, an interdisciplinary tale. Uh, this talk will be mostly talking about how robots evolved over the years and where we are today, and uh, how robots are becoming smarter day by day, and what they're comprised of, and what we can expect in future. So it will mostly be an overview talk, slightly touching upon the key areas of robotics and AI, but not going much into details, because we have to cover in time. So here is Shan Paul. And along with me, I have Nasirul Haque, who is my longtime friend and also a colleague in TCS. So, Nasi, you may carry on.
Hi, hi. Good evening, everyone. I'm Mohammed Nasirul Haque. I'm from robotics has been a part of me since the college times, and we have done a lot of things together, and we have like groomed the juniors also to carry on the robotics discipline in forward, and then going ahead. It's a very honorable moment for me to come back as an alumni to give a talk on robotics and AI, the very hot topic of today. So, moving ahead with Shayan, we'll be starting off our presentation on this topic: robotics and artificial intelligence and interdisciplinary tale. So,
Okay, yes.
So,
So
may
we
I add
will,
something?
yes, sure.
Hello. So, thanks to the entire Robotics team and Netaji Subhash Engineering College and all those faculties who have really showed interest in this talk. And so, we are very much uh, grateful to them that they invited us here so that we can share our experiences and the tale. So, yeah, we may
Yes,
move on.
we are very happy to have you both. So, yes, generally, we will have the talk on the very trending topic from both of you. But I want to ask that how are you spending this quarantine? Only AI, robotics, or some different stuff?
No-
Okay, from my end, like mostly it's the office work. As we IT people, we don't actually get holidays even in pandemic situations. We still have to support everything, whatever is running on the world. So it's mostly the at home work from home, and the usual stories of work from home, which you see all over different channels and YouTube, how they show. So it's more or less that only same thing for me.
Work from home is yeah, that's a like whatever memes you see of the internet, uh, it's more or less like that only. So we can't stop because the whole world depends on a variety of services provided by the IT industries and the tech giants. So yeah, we have to work from our home as usual.
Okay, so now the stage is completely yours. So we are very excited to have a session with you guys. So please carry on. Thank you.
So Nasrul, uh, you
Yes.
can move the slide, I think. So yeah, you have already said that this will be an overview talk over how robotics evolved and what are the things that comprises robotics, and uh, also where robotics is applied and what will be the future of robotics. So here you can see the overview starting from origin. Then we'll be talking about the timeline, that is from the where it started and then till today, the present day. And then we'll be talking about what are the components of the robotic system and what are the paradigms that are followed or uh, conventional. And then we have this all the system like perception, planning, control modules, and we'll be talking about types of robots. Then DIY robotics, so the things that you can do at home. Then competitive, you can obviously participate in competitions and win prizes and also get recognition. Then we have applications of robotics. Robotics is now applied throughout the industry, from uh, healthcare to transportation to disaster management to everything. So, and then the need of the hour, COVID-19. COVID-19 has really been a problem to humankind as a whole. So, robotics is going to uh, help us in the situation. Then we'll be looking forward to the future of robotics and AI. So, Nasi, I think you can start with the presentation.
Yes, thank you, Shayan. So I'll be starting off with the origin of robotics. So the origin is very fascinating, as like from ages man has tried to automate the mundane tasks, the day-to-day task which a man does, be it like fetching water from the river or lending helping hand to do the human chores, or maybe like the different water mechanical clocks, or be it for entertainment purposes. So origin dates back to the Greek civilization. Like there were many mythologies regarding the robots. Like they say Hephaestus, the Greek god, he used to build the mechanical servants for the Greek people, or the Jewish clay golems which they had. Like those golems were supposed to be helping the Jews. Then we have the Talos, the bronze man who used to guard an island from the pirates. So like this, these are basically mythologies which date back to the Greek era. But along with the mythologies, we have like age-old inventors and engineers who actually developed different things related to robotics and AI. So there, like I would like to mention a few prominent people who have developed over the time. So like starting from Sebaceous, he used to make organs and water clock and moving figures using like the hydropower. Same way we have Archytas. He built one steam powered engine back when people who were not able to build proper mechanical structures. They used to use human labor as for their work. So in that era also, robots paved an important role to develop as a scope of research and development. Then we have the Arab engineer Ismail. He used to build like different objects like animals shapes like peacocks or automated gates and doors. And then he built one automated waitress. So like you must be thinking automated automation requires AI, and then it will like have computer based programs or something. But back then when computers were not even known, he built automated objects and then different structures using those mechanical parts, and then using his knowledge of mathematics and all. And he is even the pioneer to the modern flush which we use. So he, the most prominent like invention by Ismail was a waitress who used to serve drinks exactly at 7 minutes. So like after 7 minutes, the expected customers glass was supposed to be empty. So the waitress will come out and then fill the glass and then go back. And after 7 minutes, she'll return to serve. So this was like a completely automated system without any human intervention. So like back in the days of 12th and 13th centuries, then also we had these automation. And then the Leonardo doesn't need any introduction, as we all know about his different sketchbooks, like how he used to sketch the based on anatomy of the human. He used to make those mechanical robot structures and other mechanical designs, which till date many like engineers and inventors, they take those designs and then they build upon them for a better structure and then proper like solution to various problems. Then we have Lewis. He built like a flute player, pipe player, and an automated duck. The automated duck was supposed to like fetch the food from the presenter's hand, eat it, digest it, and then like excrete it. So the digestion part was somewhat fixed. Like he had a secret chamber box where he stored the intake, and then the excrete was like a separate thing. But back then in 12th and 13th century, people thinking about like such level of automation is intriguing to mankind. So from that, we are now like on the latest, we have like sensor based programmable robots, where we are like building robots using machines sensor based robots on modern electronics, and then computer based programs and different, like we implement artificial intelligence to make them more understanding more percepting towards the environment, so that they gather more knowledge and be helpful, more helpful to the human as a whole. So moving ahead, we have the timeline. So the timeline of robotics, basically it starts from 1921. So 1921, the first time robot term was used in a movie by a Kes writer, Carol. So from there, the robotics has taken up like a speed, and then like there was a downfall in between, like in 1960s, but again it gathered the momentum, and it has come till this date. So following up, like we had in 1939, Electro, the first humanoid robot comes into picture. Like it was a mechanical robot which was like no programmable parts, but it was somewhat autonomous based on the mechanical design on which it was built. Then we have the first autonomous robot which came in 1948, which is actually like a proper autonomous robot with a complex behavior. And before that, we have the like a major uh, like uh, mm, important point in the history of robotics. In 1941, Isaac Asimov, he formulated the three laws of robotics, which is even applicable till date. So the three laws goes as: a robot may not injure a human being, a robot must obey orders, and a robot must protect its own existence. And this order of three laws is very important. And in a coming up slide, I'll show you why this order is important, and like it cannot be messed up. You can like consider it as the first law, second law, and the third law of robotics. So like moving on from 1948 till in 1950, the famous Alan Turing came up with the Turing machine and the Turing test, which like the Turing test is actually the test to determine the intelligence of a robot, like how intelligent a robot is. And Alan Turing, as he is known for his greatest contribution to human history, the breaking of the Enigma code, which was used by the Germans. So from then, the Turing test is used to determine the how much intelligent and how capable an autonomous robot, or even if we are using semi-autonomous robots, how much capable they are. Then moving ahead, in 1951, we have the first neurocomputer. Then in 1954, we have the digitally operated programmable robots. Then 1956, the field of AI research was founded, and then from there, AI was also incorporated as a part of robotics development. So in 1960, we have the construction of Mark One perception, like a new computer, which was landed. It was like based on trial and error. Then we have the ultimate robot to like it was basically a stacking robot which you used to lift up objects and stack them. Then moving ahead, in 1972, the Stanford research develops Parry, like it is to simulate the it was used to simulate the paranoid schizophrenic patients, so that they would be able to study and help them with some their development, and help them in leading a normal life. And then one another very prominent uh, uh, point in history, in 1968, the first mobile robot, like the robot which could move, shaky, is introduced, and it was controlled by computer. And back then, the computer was so huge that it would fill the whole room. Then we have Skara. Then coming to 1984, then we have the CYC to codify million pieces of knowledge. Now, then we started moving on more on the intelligent robots, following ahead. So same way, moving ahead, in 1985, we have the VR introduced the virtual reality as modern days we use the augmented reality and the virtual reality. So virtual reality actually dates back to 1958. Then we have in 1986, we have the Honda creating the first series of humanoid robots which could actually walk on 2 feet. So like the first that it also marks as a major uh, contribution in the history of robotics. So moving ahead, then 1988, we have the helpmate service robot, which starts to help people in the hospitals. And then the research goes on, and then we get the AI chatbots, basically the software robots. So moving ahead in the timeline, then in 1990, we have coined the phrase augmented reality. Like from virtual reality, we shifted to augmented reality. Then in 1990, iRobot Corporation was founded. It was founded for producing military grade and domestic grade robots. Then in 1997, we have the first AI robot, Deep Blue, who defeats the world champion, chess champion Gary Kasparov in a game of chess. Then we have in 1997, even NASA's first uh, semi-autonomous robot, which was named Pathfinder, was sent for the space exploration. That was the first time when we had a successful robot being deployed in outer space exploration to now we have, as we all know, Curiosity rover is the one of the Mars rovers which NASA has sent on Mars for further exploration of Mars. Then in 1998, we have created Kismet, a robot that interacts emotionally with humans. So after all these normal automation processes like moving, obstacle avoiding, and all, then moving ahead, the main targets which we the problem statements or the main focus which we are having nowadays is more of an emotional content like how does a robot will like see a human's emotions and then perceive it and then react according to it. And apart from that, we have like this is one of the genres in which the research is going on. And with this, we have those automated cars. So automated cars, they come in like 2005. Stanley, it the first automated car. But prior to that, we have the industrial robots growing. So in 2000 to 2007, in that era, we see a huge growth in use of the industrial grade stationary robots, mainly the robotic arms in various industries, where like its primary functions were like to lift objects and then move the objects or paint those suppose some cars, if it's used in a car industry, then assembling the car, painting the car, then carrying the car. Most of them were like supposed to be given a set of instructions which it would follow and then work on it and then show the do the whole task in a seamless manner with least possible errors. So in 2006, then IBM introduced Watson. So Watson is basically a question answering computer that was you asked it some questions and then it will answer you back. So Watson was you can call it an interactive uh, application robot, which it you can interact, you can ask your question queries and it will try its best to answer based on it. So moving ahead, then in 2011 and like 12, we have the introduction of Siri and Google Assistant, the software robots. Like they don't have any hardware form, but they are in a form of a computer program, which is more built for the purpose of helping the humans with their day-to-day tasks. Like you can use your Google now or the Google Assistant right now and then set an alarm, set a reminder, make a call, and then whatnot. Like it has progressed over the years, like from 2012 to 2020, over various domains, exploiting various different fields of research and making it more better and better day by day. Then we have the introduction of Baxter. It was supposed to do repetitive tasks. Like if I give it some tasks to repeat, then it will see those tasks or perceive those tasks with sensors, and then it will repeat those tasks as we perform it. Then we have the Google Glass for the augmented reality. Then we have Alexa coming into picture, and then same way we are moving ahead in the time with all these details. And then moving ahead, we have the drones which come into picture. So the drones now, they are like a big field of development which introduction of drones came into picture. Then we have the different uses of drones in various autonomous drones can be run autonomously, and then it will use in search and rescue operations or in delivery options or in various other fields. It can be used military, security, surveillance, and we have a very big scope of using the drones or the airborne vehicles. So moving ahead, like in 2020 now and then in coming future, we have a huge growth and huge domain for the robotics to flourish and then be explored and more get incorporated more into our lives. So moving ahead, in the starting, as I mentioned, like why Asimov had put those three laws in the order he did. Like the main reason for putting it in that order is, as you can see, like if we change the orders here, then you can see there are more anomalies which comes into picture. Like in the second picture, if you see, if we change the order as like first we give don't harm humans, then protect yourself, and then obey order, then protecting itself will come as a priority over obeying order. So if a order is given to a robot, like if technically speaking a robot is able to understand your orders, then if you give it an order to do something, and if it finds that that thing is going to hamper its very existence, then that he'll not do that task. So many of those tasks nowadays which we used the robots, like for deep space exploration or for different and for many different search and rescue operations and everything, so there he'll yeah. And then moving ahead, if we even if we, as you can see on the screen, if we change the orders in that manner, there will be a lot of chaotic situations which will come into picture. So the Asimov's laws of robotics is basically from 1980 to 2000 we saw a negative robot building and the research and development, more companies started uh, um, more companies started pouring in funds for the different research to the different companies who were or different colleges who were researching on the use of robotics and everything. So this is basically the timeline from 1950, the first existence of an industrial robot, to the current time, that is 2020, the whole flow of how robotics originated and then how it moved ahead, and the present situation, what it is now. So, moving ahead, I'll hand over the next slides to Shayan, and he'll be taking over from here for next part. So, Shayan, over to you.
Hello, am I audible?
Yes, you're audible.
Okay, thank you. So Nasirul has already covered the timeline of robotics and how robotics came into existence and how it has evolved over the years. Now let's see what's under the hood of a robotic system, or what comprises a robotic system. Uh, so this is a very simple diagram, and so by robot we understand that it has a physical embodiment in the real world. That is, it it is an agent that is physically present in the real world, and it can perceive the environment. That is, it can understand the environment, how it is. It can see or hear or feel uh, what the environment is, and think upon that, plan something, and then use its effectors to do some actions on the environment or the world or the surrounding environment, you can say. So so you can see the robotic agent has sensors and effectors. Sensors perceive the environment, and effectors, or the actuators, you can say, um, take actions on the environment. So this robotics system, developing the system is actually requires knowledge of various fields and domains, mainly comprising of the computer science, electronics, and mechanics. So in computer science, we can say the artificial intelligence, algorithms, and all these things play a huge role in robotics. And electronics, you have the signal processing, and then control systems. And mechanics, you have knowledge of kinetics and dynamics. kinematics and dynamics of the system. So moving on to the next slide, you can let's see what are the robotics control paradigms. So here you can see a robot trying to place a bottle at a specific position in the on the table. So now robotics control paradigms can be of three types. Okay, hierarchical, reactive, and hybrid. By hierarchical control, you can see it senses, then plans, and then acts on the environment. So it's a like linear flow. uh, it cannot directly act on the environment. It has to do some deliberative processing on the sense data and then do some actions. This type of systems were used in the classical robotics systems in you can say the 70s 80s, and then once the sensorized robotics have started in late 1960s. So after and parallelly, there was another paradigm that is reactive, which says ki you directly act based on what you sense. So it's more like you can say it is analogous to our reflexive actions or reflexive behavior that humans or another animals portray. Like if you touch fire flame and then your hand will instantly move away because of the reflex action. So that type of reflexive behavior can be seen as a reactive control in robotics. So, suppose um, there is an obstacle in front of the robot and it has to avoid it. It didn't plan actually beforehand. The obstacle will be there and it has to move in a certain path or something like that. So reactive paradigm more or less covers that. And then we have the hybrid. That is what actually prevailed from the late from the 90s to till now. That is mix both of the systems, like uh, do hierarchical and reactive in parallel fashion. Like you understand the environment and you have a mental model of the environment and you plan on the basis of that. But in case something changes on the go, you can act accordingly. You can sense it and act accordingly if something goes out of your plan. So then let's move on to the next slide. So here we are going to start with the perception, the first module of robotics. That is how the robots need to feel the environment. Like so, by perception, it means the robot needs to understand the state of the environment or its own state, like where it is and or what is its position or orientation to the with respect to the environment. Hmm. And also its own state. Own state means like you have like things like whatever is internal to the robot, like uh, its own speed or orientation or the like batteries remaining battery status. Okay, so we have this type of sensors, like we have proprioceptive sensors. By that we mean that which this type of sensors measures values internal to the robot. Man, it helps to understand its own state, that is the motor speed, odometry, direction, orientation, battery status, etc. Using IMU. IMU is International Measurement Unit. It comprises of accelerometer and gyroscope. So accelerometer actually measures the linear acceleration and gyroscope the orientation. Hmm. So together they can identify the uh, pose of the robot, and also it compass also helps in it to understand the heading with respect to the Earth's magnetic field. And then we have this wheel encoders, which actually or joint encoders, which actually take into account how much distance the wheel has traveled or how much angle the joint has moved. So this type of things. Then there are exteroceptive sensors, which are used for understanding the environment. So like distances to object, intensity of the ambient light, and other unique features, some landmarks or something. Like you have ultrasonic, which measures distances via like echoing sound. And it it actually measures the time taken to have a round trip of the sound emitted by it. So the ultrasonic sensor emits a sound by its transmitter, and then it receives by its receiver, and the time taken by it to it calculates the distance to the obstacle or some the environment, whatever it is looking at. So then lidar is like light detection and ranging. By lidar you can calculate the depth of the A, and you can generate the point cloud of the whole 3D world. And then you have infrared for various purposes. We have cameras, the one of the most important sensors, exteroceptive sensors. Cameras provide visual feedback. It is vision is a very important sensory feedback to the robot, because it has a rich information which can extract with a variety of algorithms available today. Then we have microphones to understand for sound, tactiles for touch. Then we can also classify sensors in passive and active. Passive is that measures the energy coming from the environment. It doesn't emit anything, like cameras, tactiles, or like whichever registers touch. Or and active sensors which has their own transmitter which emits their own energy and then measure the reaction. That is ultrasonic and lidar, which have transmitter receiver pairs. Okay. So moving on to the next slide. So this is how perception works. Like first you have raw sensor data. So you have this vision, lidar, sound, IMU, and etc. Which is like you can see the top row two pictures. Left side one is the IMU data, okay, and the right side one is the uh, lidar data, okay. So this is what the raw sensor data looks like. But to understand it, you have to find out some features out of it. So you do a feature extraction and try to understand the lines, edges, colors. Okay, phonemes when like sound, from sound you extract phonemes. So you cannot directly extract words or sentences from sound. First you have to extract phonemes. Okay, so and then IMU we can understand the position. These are the low level features. Okay, and from these low level features you can further extract into high level representation, which are like objects. Like you can see the second row, left one, you can have a like car. We can use an object detector to identify a car. And then right side you can see semantic segmentation, so which actually groups the pixels into the categories. So these are the landmarks. And then you have words. Okay, from phonemes you extract words, and then from position you extract trajectories of things moving around in front of you. Hmm. You can extract all these things. And then you have to understand the state of the environment. Okay, and now by state estimation, it is like where is it actually in the environment, and what is its internal state. So state estimation is a little bit different from feature extraction. It's more based on beliefs and understandings, where it is, and trying to match with the world model or the map. You can see there is a world model, maps, and knowledge base I've mentioned. So actually the high level representation and the state representation of the environment both um, considers the world model, maps, and knowledge base to extract things and estimate the state. The world model, maps, knowledge base, this can be prior information. You can feed all these things prior to the robot going live in the world, or the robot can understand the environment and start creating the model of the world or the map, storing it in a knowledge base, and then using that information to estimate the state of it in the in future. So the next we have this I hope you all can follow up till now. It would be good if you can reply. And then perception, we have this, like we're taking the case of an self-driving car. Suppose though self-driving cars are not yet level 5, we have level 3 self-driving cars, which are like you can say semi-autonomous. Okay, we can do, which can do some things on its own and which cannot handle some of the edge cases. And here we have like stated that two simple things like object detection can be done using like state of the art deep learning computation techniques like YOLO, first RCNN, SSD, etc. So if you can, if you don't know about this, you can look up into the internet, and yeah, because we cannot cover all these things in this short time. And then there are lane detection. Lane detection can be done in various ways, but we can use classical computation techniques like canny edge detection, and then followed by a Haas transform to get the lines. And then after lane detection, we can do lane following, though lane following is not covered here. Okay, so classical computer vision techniques are lightweight in nature, so so wherever it can be done with reasonable efficiency, we can use them. And wherever learning based techniques, learning based AI techniques, deep learning or machine learning based techniques excel, we can use that to extract the features from the environment and then estimate state from it. So for localization, we can use the GPS, though visual localization can also be there at a finer resolution. Uh, so that is another topic in its own. And then we have the depth data. You can see that how the cars, self-driving cars, see through their depth cameras or lidar. This is actually in a in a different color map, so you can understand the different. Actually, I mean, normally it's a grayscale image, but here it is mapped to some colors, some color map, so that you can understand that some when the car is at a little far away and this side car is nearby. So this type of data is needed to understand it in the 3D world. Okay, and planning. Next is planning. So we have mission planning, and then we have motion planning. So mission planning is the like main one, and which controls the motion planning. So now we know the state where the robot is. Okay, uh, we assume that once the perception task is done, we assume that the robot knows the state of the environment and itself, and then it also knows where to go, because that is what is needed for a planning task input, and then or what to do. And we also need the motion model of the robot, that is how I mean, describing the motion, the kind of kinodynamics. And by mission planning, we understand it is the tasks, objectives, or actions. That is the high level tasks or objectives. Like if for a like interactive robot or a human robot interaction scenario, like you can say like bring me the bottle, or go near the chair. Okay, this type of things, like these are the tasks or the objectives, the high level. Yeah. You, on the right hand side, you can see a picture of the Flipkart or Amazon warehouse, where these robots, multiple robots, are actually going around in the environment and doing picking and placing tasks. Okay, sorting, all these things. Which robot will pick up which parcel and drop where, uh, 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 and all these type of things are in the mission planning. Okay, that is it's a like multi-robot system, where all these algorithms decide that which ones will do what tasks. But here we'll cover the motion planning part, where motion planning is the low level control planning, which is once the task is set, and then motion planning is how to do the task, how to, like if it is a navigational robot, how to navigate throughout the environment, avoiding the obstacles through by choosing some paths or deciding some trajectories. Or if it is a manipulator robot, then uh, how to manipulate, how to pick an object and place another object, suppose like grippers or robotic arms, uh, and doing it very graciously, without colliding with all the other objects in the environment. So it is planning how to go from state A to B by taking some actions. Okay, and we are subject to the constraints of the environment. So the environment has some constraints like physics related constraints, so which we cannot avoid. Suppose the robot may have some constraints too, like the robot may move, the robot's motion may be some type, like it can move on only forward and backward, it cannot move in sideways. That are constraints. Okay, that are constraints of the robot itself. So constraints of the robot and constraints of the environment, where it can reach and where it cannot reach. But overall, if you see, the problem actually boils down to an optimization problem. So this is one approach. Other approaches can be taken. So by optimization problem, we can see that we can minimize the cost associated with it. So it can be like time, distance, or energy. By energy, we mean like the battery power. So and then within some constraints, subject to constraints, we will minimize this. Then next slide, we have this thing called understanding the state space. So we have the state space. But now a representation of the world without the robot. State space is that either free or occupied. When like either the state, some areas are blocked by obstacles and some areas are free of obstacles. That is a representation of the world. And then I'll go to configuration space. First, I'll tell you the aim of motion planning is to find a feasible path or trajectory that satisfies the constraints. Okay. Now the thing is, we have a detailed representation of the world in maps, models in this format. That is stored or like uh, in the robot. It has either learned or we have as a priori information. Okay. So, but we need a simplified representation, and the simplified representation can be something like uh, which actually gives you the state of the environment at any time t. Okay, so we have state space and configuration space, c space. So from that we can even further boil down to discrete representation of the world. So now before going to discrete representations, first we will see like what is c space and what is state space. So c space is state space plus robot state description. This is the pose, geometry, and constraints. Like see the robot, you can see the yellow robot, and it can the cream color portion you are seeing, that is the actually configuration space free area, and the light blue area is actually free space. It is near the obstacles. It is so near the obstacles that any robot, if it tries to go inside that area, it will collide with the obstacle. So you can see the invalid robot configuration. So we will actually, when we are planning something, we will actually consider the obstacles to be a little larger than what it is in the real world. So that is what we will do. We will grow the obstacles by the diameter of the robot. Okay, for a symmetrical configuration. Okay, and then here you see that from simplified representation of the world, we can go to discrete representation of the world. Why discrete? Now you can say, like you can work with the state space or c space, but the thing is, the continuous representation of the world that we have, if we discretize it, then it will be easier for us to apply all the computer science algorithms or the things that we already have um, to make use in this planning task. So we can discretize this into grids or graphs, like 2D grids or graphs. Okay, in the grid, each cell is, like you can say, either occupied or free. So from in a grid world, you can go from one state to one cell to another. So you can specify the state transitions from one cell to another, and there is the graph. Like you can generate a graph from the grid, or you can generate a graph by sampling points over the C free space area, the configuration free, those places where the configuration of the robot is valid in the environment, that it is not colliding with some obstacle or something, some part of the robot is something. So, and then once we have the graph, we can generate plans accordingly. Like we can use graph search algorithms. Like here we will see, once we have the grid or graph representation, it can be easily solved by frontier based methods like flood fill or graph search methods. Uninformed study, you have studied, like the computer science people may have studied, or some other departments may also know. This is Jigsaw's algorithm for finding shortest route in a graph. Then you can use heuristic algorithms for getting some prior understanding, like hints that whether how much close you are to the goal, so that you don't have to explore the entire state space, or all that more nodes in the graph. So we have a global planner, we have a local planner. The global planner takes in the grid or graph representation of the map, and it runs at a low frequency, because it doesn't need to run at like every second or something, or every half a second or something. It runs after a interval of time and generates a plan, uh, how it will go from, suppose, Q start to Q goal. You can see that. So once it generates the plan, it transfers the local planner also goes on simultaneously at the same time in a high frequency. What it does, it takes in the raw sensor data and provides some reactive control. We have seen like hybrid control paradigm in the previous slides, where I'm saying that like hierarchical planning is plan and then act, and here you have the local planner which acts whenever it faces something in the environment. It directly senses and acts. So like you can have some collision avoidance algorithm, like if any dynamic obstacle comes in your way, like here you can see the intruder. Okay, so you planned the global trajectory, and it came in your way. You didn't plan for it. It was not previously there, the intruder. So you have to act accordingly and find a local trajectory to avoid the obstacle. Okay, but this type of things actually doesn't work well in this grid based algorithms doesn't work well in high dimensional configuration spaces, like where in this is a 2D configuration space you are seeing. But in higher dimensional configuration, when you are dealing with manipulated robots, which have like 4 to 5 joints, so you have to consider all these degrees of freedom, and it will actually increase the higher dimensional. It will increase the dimensions of the world, C space world. So there we use probabilistically sampling techniques. So anyway, that is out of scope of this talk. So we will go to control. Okay, next. So we know um, that once we have the plan, now we have to execute in the real world. But it may happen the plan may not go exactly well, or because of uncertainties in the environment, the real world is uncertain. uh, so we have made a deterministic plan. We didn't incorporate the probabilistic nature of the environment. So for that we can use this we can use all these probabilistic methods also. But the main thing is to control the actuators. You need control algorithms, which is like you want the motor to rotate for something, or stay at some position, and it is not doing that. So you need some control algorithm to make it come to the desired state. Like you can see the inverted pendulum example. So we want that pole, that inverted pendulum, to stay upright. And when you are giving forces from the left side, right side, getting imbalanced, and the control algorithms is trying to make it upright again. So this is what we need. Suppose you are following a line, then or something following a lane. Okay, then the thing is you will have errors in your you generated a plan, you generated a trajectory according to the planning module, but you may deviate from that. The controls algorithms will try to make you come back to the desired state. Okay, and then so so you need state, the current state at the time t for control, then the dynamics, how the state changes over time. Okay, then reference, like what we want the system to do. For example, in the inverted pendulum example, we want that to be upright, straight, okay, at 90 degrees. Okay, that is the reference. Output is measurement of some aspect of the system. Suppose, like, we can say what is the current angle at which it is after the control, after the actuation is done, after the actuators have performed something. And then input control signal, the control signal that is inputted into the controller. So, and then there is feedback. So feedback is mapping the output to the input. Okay, we the actuators do something in the environment, and after that you need to understand what is the current state of the system. Okay, the actuators have done something, but is it already at the desired state? Is it already at the state where, when the reference point, or it is at some deviated position? So you need the sensors to give you the feedback. Suppose you want your robot to go forward 10 meters, but the robot goes up to 8 meters and stops, or goes 11 meters, something like that sort of. So you need to understand that and provide that feedback through sensors, through wheel encoder, suppose, or suppose servos. And then this feedback is fused with that input and fed back to the controller, so that it can bring back the system to the desired state. So there are actually two types of controllers: feed forward and feedback. We are not covering feed forward here due to lack of time. Feedback is more used, and it is widespread. So I hope you could understood what I showed you. If you have any questions, you can ask. I'll try to answer that. And the next slide is the types of robots, where we have this wheel. So we have seen how robots are made. So we have this type of robots. Okay, we can classify the robots based on the locomotion. Okay, the wheeled robots and legged robots. If they have actuators used, are wheels, then it's wheeled. And if there are legs, for legs we need servos. Because then you have this stationary robots, which are manipulated robots, which pick and place tasks, or, like, you can say, in industrial robotics, many types of things like welding, okay, sorting. These sort of things are done by manipulated robots. Then we are flying drones and quadcopters and all those stuff come into that. And then we have mobile manipulator. If we attach a manipulator to a mobile robot, it becomes a mobile manipulator. And here you can see the rover kind of robot, which is on Mars. And so this is of space robotics, actually. Anyway, this comprises the types of robots, and after that, Nasirul will walk you through the next few slides. So, Nasirul, you can take over from here.
Yes, Shayan, thank you for the informative session on how robots see the world and how do they act and what do they do. So moving ahead, now we will be looking at till now we have seen only the theory section on how we see the how robots see different places and how they perceive the environment and how they act on it. So next, what we will be discussing about is how will you be able to build such an such a robot at home. So that will be like the DIY part of the robot. So in the DIY section, we have uh, like a different like as I mentioned the different perception modules or different sensors which we use. So we have different IR sensors, and then We have the camera module, as Shan mentioned, like we are using the camera module. So the first one which you can see, this is basically an IR sensor, which is based on like a light and infrared light being sending out and then receiving it back via the receiver, and then based on that the calculations are made as to like what is the nature of the object it is looking at. The second module which you can see is actually a camera module, which you can take in those images and then use an image processing algorithm or some processing algorithm based on image, so to like feed the robot and then act accordingly. Then we have the chassis, the general structure of what we have for a chassis. So here we install all the components and then put it together, and then we make the give a robot a base on which it will all the parts will be assembled. Then we have the Raspberry Pi and the Arduino microcontroller. So Raspberry and Arduino, they have multiple different types of controllers. Like we have the Raspberry Pi has different versions, like the latest one being 3B. And then we have the Arduino, like we have Uno, Nano, Mega, and then there are lots of other microcontrollers with different set of capabilities and features on it. So these microcontrollers are basically, you can say, like the motherboard of the robot or the brain of the robot. So after the the sensory input, all the data will come to the microcontroller. It will do a calculation, and then it will process that data and give an output to the actuators. So the actuators can be in terms of motors or different servos or everything. So here in the bottom right corner, as you can see, in the bottom right corner, as you can see, like there are different types of motors which is being shown. So we have stepper motors, we have the normal DC motors, we have servo motors, we have low power motors, we have high power motors. So all these the motors, they are controlled by the microcontroller. So the microcontroller, it is like the, like I mentioned, it is like the brain of the whole robot. So that is you can correspond it to the brain of a human. So like a human uses all the processing and everything is done in the uh, brain. So similarly, all the processing of the robot is done in the uh, microcontroller. So those motors which we have, so these motors are basically, they cannot be directly controlled by the microcontroller. So we have something called motor driver, which acts as a bridge between the microcontroller and the motors. So as you can see here, the bottom left three pictures, the blue colored board and the two red colored boards. So those are basically the or the chipset which is responsible for controlling the motors based on the input from the microcontroller. So we have those ICs which are responsible for driving the motor, giving the power, and then we have multiple types of ways of giving power to the motor. So these are the few parts. Then along with the motors for movement, we have the wheels. So in the left side you can see like there's a collection of different types of wheels. So wheel can be like any circular object which you can attach to the motor, and it makes a robot mobile. So along with all these things, the robot to run, it needs power. So the for the power we may use like the AC adapters, like how we power our television, how we power our Wi-Fi's. We have adapters, or how we charge our mobiles. So in that way, this we might have batteries, or we might have adapters which are taken so from a source, like current from the source, and then it those powers which it gets, we can provide a good power battery for power, and then we can have these in the center, as you can see, a digital display unit with a digital display. This is actually a power controller. Like it controls the amount of power being fed to the different parts of the robot. So this basically controls how the outburst of power, or if there is any fluctuations or anything. So these are the basic parts which you can actually find in the market, or you can buy them online and build your own robot. So like you can start from a simple robot which can avoid obstacles, and then move ahead and build a complex swarm of robots if you can like interconnect them using, there are like various modules available in the market. We have the Wi-Fi modules and the Ethernet modules which will help you connect it to the internet. So once if you connect it to the internet, you can have your whole like a group of robots connected to the Wi-Fi system, and then they will interact with each other, and then they will perform a particular task in a unified manner. So moving ahead, we have like along with the DIY, we have many competitions in different fields of robotics. So like the most common ones I'll be mentioning here. So we have the the very common one, which is the line follower robot. So this line follower robot basically it its task is to follow a particular line. It can be a white line on a black background, or a black line on a white background. So based on the sensory input, like I mentioned, the IR sensors, it will detect the line and then follow it autonomously without any human intervention. Similarly, from a line follower, we can have a little complex robot which can be a maze solver. So maze solver, like as we have seen in the small, when we were small, we used to find the path through the maze, or we had different storybooks, or in the newspapers we get these problems where we have a maze structure in which we have to find a way out from the center, or from the edge we have to find out how to go to the center. So the task of the robot is basically same here, like it has to find its way from start to end in as finding the shortest path through its whole travel set. So normally what we do is like we travel across the whole explore the whole maze, and then we again start from the first point, and then go back to the go to the end point in the shortest path possible. So as we have a 2D maze, we can have a 3D maze, in which instead of light sensors, we might be using ultrasound sensor, in which we have to navigate our way through a 3D space. So moving in more complex, we have those autonomous sumo wrestlers, like the normal sumo wrestling which is there. So these are basically bots competing with each other autonomously without any intervention. Like it has to stay within the ring, it has to push the other bot out, and then block its blows, and then we can have multiple different sports activity based autonomous robots. So next, moving on, we have like different competitions in which we have task oriented robotics competitions, where you are given a particular task which you have to solve using a robot which can be autonomous or semi autonomous. So the task oriented roboting can be here we have an example where the robots are supposed to sort the yellow with the yellow objects with the white objects, and then collect them. And maybe we can add more features onto it, like counting how many yellow objects are there and counting how many white objects are there. And then moving ahead, we have another line follower based competition, an example. So where you have to pick up blocks and then place them in the broken paths to complete the path, and then it will send a sense an information back to the other robot, and then it will complete cross across those paths and then complete the task given. So these are like basic competitions which occur across regional level, or in national level and international level. They hold up very different prizes based on where it is, who is hosting it, and many get good innovative ideas come out via young minds, or research based different companies. They also take part in it and then try and solve the problem in the most in the best possible manner. So moving ahead, the next which comes in the is the application of robotics. So we till now we have seen like robots has been like how to make the robots and how to make your robot at home. But there must be some business value to these robots being built or being researched on. Like it should provide some value to the customer or some value to the humans. So based on that, we have like various fields on which like robotics is implemented, and then we have those smart robots in the industry which help humans do their task easier. So we have like robotic vehicles. Those are like self-driving vehicles. It can be delivery trucks. It can be like different big trucks or the shuttles which we can use like autonomously, and then there's no driver in it, and it will navigate through the path as Chan mentioned before, using lane following. It will follow the other vehicles or follow a particular lane and then reach the destination. Similarly, we have the customer service robots, which are not so much prominent in India, but outside India, mainly in Japan, we have this very common, the shopping assistant and promotional robots and tour guide, where like the instead of an actual person being a tour guide, there is a robot which guides the tourists across various places, and then based like on the tourist queries, it will give you answers. And then like it is more designed in a fashion to imitate an actual tourist guide. Then we have promotional robots which will go on advertisement, like it will run through the streets and with an advertisement on its screen and then show everyone. Then those are actually like all the autonomous robots, like no humans control them or drive them through the streets. Then we have the shopping assistants, like instead of actual person helping you, we have a robotic assistant. Then we have in the industrial use, where we use the for welding, industrial cleaning. Then we have laser cutting. Apart from that, we have heavy lifting, and then all the things which are like mundane in nature, or like they have a fixed set of procedures to be followed, or where we can incorporate artificial intelligence into the robot, and then it can learn from its experience, and then like provide its further, like it enhance its work nature of work, and provide a better solution every day without any human intervention. Similarly, we are in from industrial, we have in logistics purposes also, where we have the sorting robots. Then we have self-management robots. Then we have different conveyor service, where like these are commonly used in like very big warehouses. The most common markets where companies which use these are the Amazon, Walmart, Flipkart. They use these robots to sort the items based on maybe weight or like where they are shipped to, and they will just like have a swarm of robots working together, like storing everything, and then when which is required, which is to be shipped, it will fetch all those back. So there is no human input in that as such. Like no one is controlling those robots, they do it on their own. Like they have a central control system which manages all those robots, and they interact among themselves also if required. So if we remove those human intervention, then we like decrease the causing error to the system. Then we have in the construction field, then we have in the agricultural field, we have in the security field, telepresence field, entertainment field, food processing field. Like most of the fields today, they have like incorporated robotics in some way or the other. So moving on, I will show you some examples of like actual robots being used in the industry. So starting off, we have the industrial and the logistics robots, which used for the manufacturing process. So this first picture here, it shows a group of stationary robots which help in assembling in the assembly line for assembling different parts to the car. Then in the second picture, we have welding robots which helps in welding the parts. In the third one, we, as I mentioned, like we have sorting robots which sort different objects. So this third picture here is responsible, showing depicting the typical warehouse of Amazon or Walmart or Flipkart, where robots are used to sort those packages and then collect them in a place, and then from getting it ready for shipment and all those purpose. Then we have the fetching robots. So fetching robots, they like fetch the supplies from the store to the stationary robots for them to like pick up and place. So like they are also autonomous in nature. So this one is an example of a BMW warehouse where this robot is tasked to fetch the parts, maybe screws or different components for assembly line. The next one is an is inside Amazon warehouse. So the first the top right corner picture, it's like you can consider it as a modified picture where we can see a robot clearly carrying some items on its top to the sorting place, or where it is tasked to like place or pick up from there and get it to somewhere. Then we have the conveyor belt. So some warehouses, instead of opting for mobile robots, they use conveyor belts which switch in lanes. So you can consider these as railway lines. Like as railway lines, they have a network and then they keep switching between different lines for different trains. So you can consider it working in that way, except for this, that they don't have any human intervention in between. Like they autonomously do this whole process. Maybe if they are doing it by weight, so there will be a weight sensor where it will like detect the weight and then move ahead. So next we have it in the defense, disaster management and space exploration. So in defense we have the military robots. For disaster management we have drones, we have snake robots which go in the rubble and places where human cannot reach, or it is poses a security threat to the human. They can send in the robots and then check for survivors or the state of the the rubble or the problem or the disaster, how bad it is. Then we have a security robot called Nightscope, which is in production. It provides surveillance to the airport security. This is currently being used at Dubai airport. So they move around and like based on its prior data and then its learning algorithm, it will try and detect if someone is being suspicious or someone is like without proper it will try and detect the actions, and based on the actions it will give a take a decision whether that person is doing some suspicious activity or he is okay to go. Then we have the curiosity rover, like I mentioned before, in for the Mars exploration. So this is also a robot which is semi-autonomous in nature. Like a human can also drive it, and sometimes it runs on its own. Like it will go for look for the sun and then uh, capture the pictures and then use the soil samples, send back those results, and then depending on the terrain, it will adjust its trajectory and then give feedback and those things. So, and the last one, which depicts as a firefighting robot. So this basically, instead of fire engine may not be able to reach all the places, so they have these small robots which they can like detect fire. They can use the heat sensor to detect fire and spray water at them. So without a human intervention, they can automatically douse the fire and the flames. So moving ahead, the most posh area of robotics is the vehicles and the customer service robotics. So this is taking quite an limelight in modern days. So we have the self-driving vehicles from Tesla, which is already in production. Then we have the delivery robots from FedEx and Amazon Prime, which actually is in beta testing now. So like they are planning to use these robots to deliver the packages across the neighborhood instead of an actual person going and delivering it. Then we have the receptionist, which who can be a robot. It can be a humanoid robot which will provide information to the customers. Then we have the restaurant service robots which will cater the customers who are coming there. Then we have the shopping assistant, as I mentioned before, who will assist you in shopping as to where you have the discounts, where you will get this product, where it is lined up. It will take you to different parts of the store, suggest you things based on your mood. It will detect whether you are liking its suggestions or disliking its suggestions. Then we have the drone delivery robots, which is also in beta testing now. So after the COVID pandemic, these the delivery system, like automated delivery system from Amazon and FedEx, and then the drone delivery system has hit a good amount of demand in nowadays, so that people can maintain the social distancing whilst carrying their activities and not hampering the services. So moving ahead, like the last section of the application of robotics which we have is the telepresence, agricultural and food industries. So telepresence is basically where we a person is not actually present there, but in a virtual form he is present. Like we can have a conference meeting where a person can be on a video call attached to a robot, and that robot might move with the person who wants to show the facility or something, while he the actual person might be sitting somewhere else in the world. So this assists in the, like this is also very helpful in today's pandemic situation, where you don't have to actually visit the person to work on go with it. So moving ahead, we have the agricultural, in agricultural background we have those weeding robots, we have pesticide spraying robots. uh, so these help the farmers autonomously do the mundane tasks like spraying of pesticides or weeding the crops, and those sections. So along with the teleconferencing, we have the teleoperation robots also. Here is the example of Shadow. So this is basically, it will imitate your hand movements at a different part of the world. Like I may be sitting at my place and I want to do a handshake with someone sitting in America. So like we can use this teleoperation robot to actually imitate what I do sitting here in a completely different location. So and we have these food processing robots also. So these food processing industry, these robots are used in the assembly line to cook the food. We have the pizza making robot, and we have very common nowadays the omelette making robots, which they cook food for the humans instead of the chefs. So these are completely recent in and under research and development. So they'll be we'll be exploring a lot in the coming years on these different types of robots. So these will ease the human workload by helping them in cooking and different services. So we have even the smart robotic vacuum cleaners. So after all these, you might be wondering, if robots will do all the job, then how what will humans do actually? So as you can see, if I'm to say, if a human robots take all the jobs, then there would be a part where it would require a human to take on the "I am not a robot" box. So basically, the underlying statement for this is that even if the robots take over the different jobs, humans will actually not be jobless. I think so. I read a comment in the comment section where Baisakhi has asked, if assuming the robots will likely replace most jobs, what kind of impact will nature of robotics industry have on the environment? So the robots are actually made by humans. So to build a robot, you will need a human. Currently, there's no self-building robot system, like a robot building another robot on its own. So anyways, even to have the master control on the robots, you will need the human. So humans will be less prone to the dangerous zones of working, or some mundane tasks, or some repetitive tasks, or some tasks which actually don't require so much of intelligence, or it's more like a factory work, just picking up and stamping the parcels as it passes by. So these are the tasks which will be mainly taken up by a robot. and there might be cases where a human like he'll get more time to relax, be less stressed, and then be and the whole for the companies, the whole service line would be less error prone, and the humans, they can relax a bit, they can supervise those robots and then see whether the work has been done properly or not. So so uh, like even after the robotic age comes into play, humans will not actually go out of jobs, and there will not be so much of unemployment as the world sees today, with the threat of robots being taking over their jobs and making them unemployed and such things. Because ultimately robots, they don't work for themselves, they work for us humans only. So moving ahead, I'll hand over to Sayan. So he'll be taking up from here.
Hello, everyone. So, well, we know that COVID-19 pandemic has seriously created a trouble in the world, and it has forced humans to work from their homes and also maintain social distancing. So, in this era, robots are a very important thing that we need right now to be deployed in various sectors of the society, and we are already seeing this happen. Like we can see that various warehouses, that Amazon, Walmart, and all, are actually using more robots than they use in normal times for sorting, shipping, and packing. And all those things are getting more automated and more teleoperated from our remote place. And those persons who want to visit somewhere, experience the world in in in, in 3D, can use telepresence robots and avatars to actually uh, feel the the world at a remote place. So they don't have to go out in this COVID-19 pandemic. This type of things are coming. Like you can use your VR headset and also put on some haptic gloves and then do some operation at a distant location from the comfort of your place. So this type of things, and teleportation robots are also used in all those factories and all where human gathering is not suitable right now. So, and contactless operations, deliveries, like the drones and the vehicles which are not yet fully autonomous. Fully autonomous vehicles will be coming later, because to be autonomous, AI has to progress, and the we have to solve a variety of real world problems that roboticists have to face in the real due to the uncertainties of the environment in the outside world. So for the time being, semi-autonomous robots can do a lot of work. Like teleoperation, telepresence robots can aid humans to do the job. Like my colleague Nasi said that the jobs will not be replaced. Yeah, actually, it seems like the jobs will be replaced, but you can see the robot maintenance and the robot development and housekeeping, all these tasks will be there. It will be not like machines will take over in just another day on something like that sort of. And you can say robots will augment our tasks so that we can be more productive and be more efficient without losing our comfort. And here you can see the third point here, where we are saying key humanoid robot is deployed in AIMS, where it monitors and collaborates with patients. So now all these hospitals and all, they are using thermal screening and all those offices, so they can deploy the bots which can do it on behalf of some human. So the humans don't have to, the security persons don't have to do it manually themselves, and they can also move around the place and also disinfect and sterilize the floor surfaces, so without involving any humans in it. So this is very safe. Like, So and we can also opt for more contactless options in grocery stores as the robotics and AI progresses. So we can order things and from like various stores, online stores, and um, these robotic systems will be deployed, which will be either aerial or ground vehicles, which will autonomously deliver and drop the ordered item at your doorstep. So, so this type of things are very suitable for in this pandemic situation. So it's like a push. It's like a necessity. Necessity is the mother of invention. So COVID-19 is actually pushing the robotics research and industrial development in this regard. After all, the bots can get infected with COVID-19, huh? So yeah, so that's the main point. Next, we'll move on to the next slide, where we are talking about the future of robotics and AI. So, though we have touched upon all those primary key points areas, so we have seen that the the progress of robotics is hugely dependent on the progress in artificial intelligence. So artificial intelligence actually comprises of a lot of things, from classical AI that you use search techniques, heuristic search, and all. You have reasoning. You have uh, logic based things, and then here you have neural network approaches, learning based approaches, and all these things combined. Then you have probabilistic methods like Bayesian systems and all. So all these things actually will evolve, and slowly as the whole uh, AI world evolves, robotics will also evolve with with it. Now there is also dependencies on embedded systems and mechanical inventions, but more or less we are quite capable in terms of that. But it's more of that key. We haven't yet learned all these things to control those actuators or all these systems by autonomous algorithms, because it requires understanding of the world in a much more deeper sense. Like we have to understand the physics of the environment. Like deep learning approaches have created breakthroughs in computer vision world, but you can see like when subjected to tasks like 3D vision tasks, it is still not performing that well. It is progressing, but we will see it do well in the next couple of years. Then I have shown you some modular approach to perception, planning, and control. Then other techniques like reinforcement learning also is also used heavily in robotics, but it is still not used in deployed world scenarios much. Optimal control systems are much more widely spread in industrial deployments. RL research is going on, which will actually which combines planning and control together, and also we will expect more end-to-end systems from perception to control in a uh, single algorithm in the next few years. As this progresses, as we can create more good state representations of the world around the robot, and incorporate reasoning into the system, hierarchical reasoning. If this happens, then that you have to do that, and you have to also incorporate the adaptive systems, because logic based things, simply hard coded logic will not work here. All these learning based things are specialized in some task, but for a robot to actually move around in the environment, manipulate something, um, you need a wide variety of skills. Like you need like grasping. It is a hard task. You need to understand how the contact forces affect the grasping of the object. And then you have like things like human robot interaction. You have to understand how humans behave around when in front of robots. And you have to also communicate effectively, so that it doesn't look like a human robot interaction in the near future. It looks like a human human interaction, more like that sort of. The human needs to there's a lot more work going on in HRI, where you have to perceive and understand what the human wants from you, and then also convey back to the human that you have understood it, or you didn't understand, and you are likely going to take this action or not. This is what robots need to do in the future. So it's these are all active research areas, like emotion sensing, collaborative robots. Earlier robots used to be there inside in industrial places like factories, and also we are seeing in warehouses, but out in the open, when they if we deploy them, they will need to deal with humans a lot more than expected. So they need to comply with social norms, and also make the humans around them feel comfortable, and also understand what they want. Depending on them, that they will take the decisions. They will, even collaborative robots will help humans to do certain tasks with greater productivity and efficiency. That is how we are expecting that the industry will move towards more robot human joint ecosystem, not like the robots taking over the humans. So we are seeing that there is a lot of research going on in locomotion, like Boston Dynamics has come up with Spot, which was released in beta for the last few months, and was released to for buying in the last week. And we are seeing that there are several self-driving cars out there, but the self-driving cars that we currently see, like Tesla, or you have seen Waymo, and then all those other manufacturers like Comma.ai and all those things, they are level 3 self-driving cars. So by level 3, it is like they have autonomous features, but they cannot do all those things. They need a driver in the seat near the wheel, and they can do certain tasks, and the driver can choose whether to give an autopilot to the system or take over manual control. But the day when the humans will be able to sleep, just put the destination in the car dashboard and sleep, will be is still in the future. It's I hope one day we will be able to do that, but yeah, the thing is still evolving. And here we have MIT's Cheetah, which is a legged robot, which have very good agility. It can move over various rocky terrains and very uneven surfaces. Now the locomotion is a very hard problem. You have to model this thing in an algorithm which understands it from the perception, the forces it feels under the feet, and what it sees with its cameras. All those things need to be processed in a multimodal fashion, and then only we humans see, like we humans feel all these five senses at the same time, and decide on something to actually do based on all these things at the same time. So more multimodal research is going on, where we can ingest those sensor data information parallelly, and decide upon something and actuate this so they will be very helpful in very unconstrained environments, like disaster scenarios, where there is no maps as such. The robots will explore on their own, create maps, store in the knowledge base, or model it, and then localize itself where it is, and then plan accordingly and take actions what needs to be done. So we have seen humanoid robots like Sophia, which has a very good emotion rendering system. The face developed by Hanson Robotics, they have done a very tremendous job, and those tiny actuators over the face can actually mimic any human expression. Uh, any expression related to any emotion, like happy, crying, or angry, or something like that sort of. So they are also developing it, but Sophia is still immobile, and they are working on those things. And so we are more to see. Sophia is also very good in natural language processing and speech recognition things. So in that front also we'll see a lot of things going on, and humanoid robots will be good to deploy in the in the real world, because suppose wheel robots cannot move over rough surfaces or uneven terrains. Okay, so like legged robots are needed, and like we can have all those type of things in the next few years, depending on the the progress in research in all those subfields. So yeah, so more or less we have covered the uh, whole journey of robotics from its inception to what we can expect it from future. So let's by this we can I think end the talk here and like move on to the next slide, which is like the questions answer. So you can ask us whatever you have, whatever queries you have. So we will try to answer them. Hello. So the question is from Indrajit Mukherjee. Uh, Although robots are there in industrial and commercial or research domain for many years, when can we expect robots as a consumer-friendly devices? What are the hurdles right now to achieve that goal? Yeah, Indrajit. So I am taking the question, Nasi. I hope you are fine
Yes,
with it.
yes.
So thing is, yeah, in industrial area, they are restricted to some confined zones. So the thing is, you can give a specific map or a model of the environment, and depending on that, the robot can be fine tuned to work there. But in an unconstrained environments like consumer service robotics, where we have to deal with humans, I just said in the last slide that this type of things like human robot interaction, emotional and sensing, then locomotion on rough uneven terrains, this type of things, and exploration uh, in an unknown areas, and adapting to the system as it changes. This sort of things, as this type of subfields advance, we will see that consumer robotics will also move. Like for example, in consumer robotics, you can understand like you want a service robot. Suppose you have a guide robot in a, yeah, although we have guide robots already deployed in the, yeah, but suppose you want food processing robot. Okay, so it needs it's a lot of dexterity. Okay, by dexterity you can like human hand dexterity, like how to hold something. Like if it makes pizza for you, then how to hold the plate so that the pizza doesn't fall out of the plate, and how to spread all those things, how to open the door of the micro oven, how to bake it, and all those type of things. These are not yet very mature at this moment. All these type of things will evolve, and we will see more consumer robotics or more robots in the out in the wild. Okay, so next.
So one question we had like from Indrajit again. If you can show up here, devices like self-learning Alexa or house help. I'm asking
Okay,
for a developing nation like India. Like, what is the scope?
uh,
I'm like, if I'm
like
not wrong, he is asking what is the scope of these devices in for development in India or being deployed and
yeah,
used in India.
like by India, are you trying to connect with the like do we have a lot of
Developing
population?
country. Ah, no,
We have a lot of
he's like,
population, and so why
he,
do we need robots? We can something
no,
like
no,
that sort
no.
of.
He mentioned as a developing country, like what is
Hmm.
the app, like how these devices are of help.
Like
So
affordability
it
or
can be affordability, it can be use base, it can be feasibility. So
yeah.
as per my view, like nowadays we see Alexa or Google Home, like these devices getting very common nowadays. Like most of the homes today, you will find Alexa or a Google Home. Anyone who is eager or keen in tech related things, they will own either of them. So in coming years, if not today, but in coming years, I'll be expecting these devices to come in the to the common household of every person for helping on the various household related tasks which can be automated. Like we have today, we have smart lights, smart fans, smart AC, even we have smart TV, smart curtains. Like basically they are trying to make everything smart and voice controlled or app controlled, or without much of human interaction. Suppose you went to your bed, you got comfortable, but you forgot to turn off the light. Then again you have to go get up, turn it off, and come back. But if you have Alexa or a Google Home, you can just ask it to turn off the light, it will turn off the light. You don't have to get out of the bed again. Or if you want to set up a routine, like you wake me up at in the morning, and uh, get up in the morning, the morning routine, and then the different lighting conditions. If you want to change how much morning news and everything, you don't have to actually read them. The assistants will read it out to you.
Yeah, yeah. So
So
actually, yeah. May
yes,
I?
Sam.
Okay. So
Yes, yes, Sam.
I think that answers Indrajit's question actually. But maybe the thing is the affordability. If you're actually asking about affordability, then as the hardware prices, as the hardware development is more, it will more evolve. The prices will get lower, and so it will be affordable. And regarding the usability, we will find a lot of uses like that will help in our daily course. Okay. So yeah, which question?
Yes.
Okay, so yeah, I'm sharing my views. Nasi, you can also. Um, so everyone is learning. What is the post COVID-19 context of future? Okay. Yeah, like I mean, ca- are you asking that how COVID-19 will affect it, the career of yours or the future? That's like that. Or I think any necessity will bring upon all these things and force humans to develop a new set of things. So AI/ML will be used a lot in the upcoming years. As you are seeing, I just showed you that robotics is actually developing fast thanks to AI and ML and everything. So and as these things evolve and progress, so we'll have more opportunities. So I think learning these things is good in the long run. I see.
Yes, Sayan. I'll based on the question, I can see like there's a great concern post COVID. Like, what will be the situation of the market? So mostly we are seeing that robot deployment is increasing day by day, given to the fact of maintaining social distance between humans.
I
So
think
for
she's
these
asking about
developments, the
career
AI
and
ML,
company.
yeah,
I think
career and
not the
so
deployment of
like
robotics. The career.
no, not. I was coming to the point where these deployment of robots will open up new job options for
Yeah, yeah,
various
yeah. We
research
mentioned in
in
the COVID
currently
19
in
slide.
research. Huh. So we have already discussed on these, like how new job openings will be there based on like if there is more robots in production, obviously you'll need to produce more, so you need job openings, you need better minds
Yeah,
to
yeah.
produce them.
That's like it goes on in a cycle. Like you have this demand, and for that you need to fulfill.
The
For
supply
fulfill,
demand chain,
the supply demand
the
thing. So
supply
I think
demand chain.
I think that will and when robots are deployed, don't expect that the whatever task the robots are doing will actually replace it, because for COVID-19 the human cannot do that task, so it's not replacing it. And if even after COVID-19 is solved, suppose for some time later, then we are the industry will try to focus more on collaborative robots. Okay, things that will help us reach and achieve those things that humans cannot do on their own. Okay, I think that's where the focus is on.
So we have one more question, I suppose.
Is robot
What is
locomotion?
locomotion?
Locomotion. Locomotion is like how it traverses a terrain, like how it traverses a surface. Like you can have wheeled robots. So wheels are used to roll on the surface, and you can have legged robots. Legs are used to, like, you can step at particular positions and go. So that is locomotion. How you traverse a terrain. Like we humans do it with legs. Some animals do it with 4 legs, and we do it with 2 legs.
Um,
This is all locomotion. Metaphors.
so it's basically movement from one place to another. So from a different set. So moving ahead, do we have any other questions? Okay,
Hmm.
so
So let's see. So hello. I think so. If you have any, I think we should wrap up slowly. And now, I think thanks to everyone who have attended this session, and thanks to all the organizers again for inviting us over here. And
yes,
so if
uh,
you
uh,
want to, if you have any other questions, you can connect us on LinkedIn, or you can follow our Twitter account. You can,
so
yeah.
yeah, or if you have any other queries, questions, you can reach back to us, and then we'll be happy to clear those queries or guide you with additional information if required. So handing over to you, Baisakhi, you can take over from here.
So it was a great event. Thank you, Shayanda and Nasirulda. Like it was very great having you here. But I want to introduce you all the two man behind this organizing this event. That is Shukolanda and Shobhikda. Without them, this
Yeah,
event
Mister.
was yes, and also yes, obviously, you three were like the main reason behind this event. So, thank you for this amazing session. And I would request you two, since you two are there, to tell something about the event and wrap up.
Here we are just thank you sir, for everyone. That my name is Sukalyan Shah.
We would like to thank Mr. Sayan Paul and Mr. Nasirul Haque for presenting such a wonderful session.
And also we would like to thank Boishaki Chakraborty for being such a wonderful and warm host.
Last but not the least, we would like to thank our viewers for being with us and making this event successful.
And the viewers, you can also comment in a comment section for your about your views, and that will be helpful for us because we can arrange that kind of presentation again. So that's it. Thank you everyone and good night.
Good night.
So, thank you, everyone. We would request everyone to follow us, like us on Facebook, and also like and share our video. I would like to thank our alumni for this warm speech. Thank you so much, our coordinators, and each and everyone of our robotics family. Thank you so much for joining this session. Thank you, and good night to everyone.
Thanks, guys. Thanks, everyone. Good night.
So thank you and good night, everyone.